My name is Adam Cooper, a rising senior chemistry major at Stetson University. This summer I was doing work at the University of Notre Dame with Dr. Maria Lieberman. The project I was working on is the Antibiotic Paper Analytical Device Project, APAD for short, a remarkable technology that can quantify beta-lactam antibiotics, which are antibiotics containing this beta-lactam ring. These antibiotics are an essential part of any healthcare system, and if you've ever been sick with strep throat or an ear infection, you might have run into the two most popular kinds, amoxicillin and ampicillin. Unfortunately, there is a large problem, especially in lower and middle income countries, that is the threat of falsified and substandard medicine. People may be receiving half the dose that they were expecting or nothing at all. There are several existing ways to test for this, mostly through the use of a large, expensive machine, an HPLC, or through a glassware assay. Now, both of these are rather expensive to set up, require trained technicians, and in general are not the most accessible technologies. And unfortunately, the countries most at risk to falsify and substandard medicines are also more likely to lack capacity to perform these pharmaceutical monitoring techniques. But what if there was a way to quantify the quality of these medicines that could fit in your pocket? Enter the APAD. Previous researchers were able to take this glassware assay and adapt it to function on paper. It works in 3 steps. The first is a base catalyzed hydrolyzation that opens this beta-lactam ring. The second, an excessive oxidation using triiodide. And the third is a back titration reduction using thiosulfate. Starch creates a blue complex with triiodide, and we use this color indicator along with varying amounts of thiosulfate to make a color code that can quantify the quality of amoxicillin in 5% steps. Now this device places the third step on paper, requiring the preparation of the first 2 in solution. My goal this summer was to optimize this device's methodology by bringing the second step to paper, which coincidentally makes the third step redundant, simplifying the procedure for the end user. So far, this reduced reaction scheme is working pretty well in a few test devices I made, though there are challenges in storing triiodide, a volatile chemical, on paper. Luckily, I'll be able to continue work on this project through the coming academic year and work on this technology that will be able to put the power of analytical chemistry into the hands of people across the world.